Hello. The proposal of this work is the determination of the horizontal wind using medium-scale gravity wave. This work was developed at the Federal University of Campina Grande. The main motivation to this work is try to investigate the interaction between the gravity waves and horizontal wind. When a gravity wave propagates in the horizontal wind, we can calculate, as we can see in this formula on right, the intrinsic frequency of the gravity wave, that is, the frequency of the gravity wave removing the effect of the wind. If you observe this formula, we can see that the wind is present, and if you have the horizontal wave number and the observed frequency, we can retrieve the wind. Thus, the main goal of this research is investigate the interaction between the gravity wave and horizontal wind in order to establish a methodology to estimate this wind. To be more specific, if we use the equation for intrinsic frequency, we can calculate the observed frequency and the horizontal wave number, wave vector, from the air glow images, and the intrinsic frequency can be estimated using the dispersion relation for the gravity waves. In this case, we have here the Gustav-Hooke dispersion relation, where the wave vector is composed by the horizontal components, but the vertical one. N square is the Brunt-Weissaler frequency that can have information of the temperature, and 8 represent the scale rate that is calculated from the ratio between the density and the vertical derivative of the density. So, m square, that is the vertical wave number, can also be estimated from the air glow image if you can observe the same gravity wave in different layers of the atmosphere. The temperature in this work, we are going to use the LiDAR measurements and model to compare the effect of the temperature in determining the wind. In the same way, the pressure is going to be calculated using the information from the temperature, using the ideal gas law and the definition of the pressure in the atmosphere. Scale rate, which is related to the density, is going to be calculated using the ideal gas law and a model like MSIS. And it is very important for our case, we have at least 2 simultaneous gravity waves in order to solve this linear system and calculate the component of the wind in the north, south, and west-east direction. If you have only one gravity wave, we can estimate only the wind in the direction of the wave. As an instrumentation, we are going to use a night sky image deployed at Cachoeira Paulista in São Paulo State, Brazil. A LiDAR that is installed in São José dos Campos. The LiDAR is going to be used to calculate the vertical profile of temperature. And a meteor radar located at Cachoeira Paulista that is going to be used to compare the wind calculated from the proposed method and the wind measured from this equipment. This busy slide shows or summarizes our observations. The first one on 14 September 2007, where we can see here the estimation of the parameters of the gravity wave on left. The kilogram methodology was used to calculate the horizontal parameters of the gravity waves, and on right we can see the wind measured by the meteor radar and the temperature from the LiDAR. More details about the parameters of this wave is going to be shown ahead. This is another case study that we are going to use here that was observed on 10 October 2007. The parameters of the gravity waves are summarized in this table, where, for example, we can see that there are two waves estimated on 14 September 2007 and two waves observed on 10 October 2007. The first row shows the parameters of the gravity waves for OH layer, the second one for OI5577, and so on. It's important to observe that the wave have almost the same period, almost the same wavelength, and propagate to almost the same direction, which is a guarantee that we are observing the same wave in the two layers. The vertical wavelength was estimated producing a kilogram in the propagation direction of the gravity waves, and from the phase difference between the two layers was used to investigate the vertical propagation of the phase, and as consequence the vertical wavelength could be estimated. In this case, the OH layer was assumed to be at 87 km height, and OI5577 was assumed to be at 96 km height. Our results shows that in the two case study, there was a significant discrepancy between the observations and the estimation of the horizontal wind. On left chart, we can see the wind, the measured wind as solid line, and the estimated wind as dashed line. The red line represents the zonal and blue lines represent the meridian components. It's clear that, for example, for meridianal component, there are in some parts of the atmosphere the estimated wind approach to the measured one. However, if you compare the zonal component on 15 September 2007, we can observe some substantial discrepancy in the determination of the wind. When we move to 11 October 2008, we can see also there are some discrepancies in several altitudes of the atmosphere. In order to investigate which is the parameters more sensitive to the estimate of the horizontal wind, we have done some simulations. Assume that the wind is correct at some altitude. We went back to the dispersion relation and using the temperature, for example, in the first case, from the LiDAR and model to see how is the importance of the temperature to the determination of the method. And we can see here that if you use the temperature measured from the LiDAR, we can reproduce some vertical variation of the wind, while if you go to the right side using the model, the estimation of the wind was almost constant for the all altitude. If we compare the density from the measured from the LiDAR with the density from the model, we could not observe any substantial difference in the estimation, as we can see in those charts. If another concern was to investigate if the determination of the vertical wavelength is mandatory for this method, and if you using only the dispersion relation to estimate the vertical wave number or wavelength and put in the simulation, we can see that there are some discrepancy in the results. And if you use the measured wavelength using the two images from different altitudes, the results approach more than the other case. As a summary, the interaction between gravity waves and the horizontal wind were used to calculate the horizontal wind, and comparison were made with meteor wind in the same site of observation. It was observed substantial discrepancy between the estimation and the measurement, and some simulations were done in order to investigate which parameters are more determinant to the present method. It was found that the vertical profile of the temperature is essential to reproduce the vertical variation of the wind, and that the determination of the vertical wavelength appears as important to the success of the estimation of the wind using the present method. There was no significant discrepancy when we used the model density compared to the observed one. This work has been supported by Conselho Nacional de Desenvolvimento Científico e Tecnológico from Brazil, and I would like to thank to the Federal University of Campina Grande for support the participation in this meeting. Thank you for your attention.